All right, so now we've talked about other things that we've done, right, with linear movement. We're also going to talk about rotational kinetic energy now. So now we're going to apply energy. The kinetic energy of an object that's rotating is the sum of all the masses times velocity squared, right? But by substituting rotational quantities, here's what we find. Rotational kinetic energy is 1/2 moment of inertia times the angular velocity squared. An object that has both translational and rotational motion also has both translational and rotational kinetic energy. So then we have to apply both, all right? Both translational and rotational. And just add them together, and that tells you total kinetic energy, okay? So we're just going to take things and mix them, put different things together to get this. So when using conservation of energy, both rotational and translational kinetic energy must be taken into account. Important. All these objects have the same potential energy at the top, but the time it takes them to get to the incline depends on how much rotational inertia they have. So we have a sphere rolling to the right, and you can see the different forces with friction included. Okay, so those are all the things we have to take into account. The torque does work as it moves the wheel through an angle. So work is essentially torque times change in angle. So force times distance, right, is work. So torque times change in angle. All right, and that tells us work, rotational work, if you will. So let's talk about some application. We got a sphere rolling down an incline. What will be the speed of a solid sphere of mass m and radius r when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls without slipping? All right, so we're going to assume static friction, so no slipping occurs. We will see shortly that static friction does no work. All right, compare your result to that for an object sliding down a frictionless incline. Be interesting to see what we can see. Do it now.
All right. So we have our rolling object, right? This, and it rolls down from a height down here to the bottom. Um, and it has an angle, and we could talk about angles, but we're going to worry more about energy here. Okay. So at the very top, all we have is potential energy, mgh. Energy at the bottom will consist of kinetic energy, but also rotational or energy that way, right? Rotational energy. So we have to talk about those two added together will equal the potential energy. And the first step in doing that is thinking about substitution. So it's a solid sphere. The moment of inertia of a solid sphere is 2/5 mr squared. I substitute that in for I. And then I also know that when we talk about what angular velocity is it's linear velocity divided by r. So I will substitute that in here. I square that to get v squared over r squared, and then I start to get rid. So my r's squares cancel, and then all my m's cancel. So I'm left with this, and I'm going to clean that up. I'm going to bring the 1/2 in with the 2/5, and here's what I get. I take my v squareds and combine like terms, multiply by the reciprocals, and then take the square root. So velocity at the bottom is going to be equal to the square root of 10/7 g times height. And this is how we can take this information and find a single equation to solve for without numbers. Obviously with numbers we can substitute and we can probably get here a little bit quicker, but that's how we get there with this problem.
And then which is fastest? Several objects roll without slipping down an incline of vertical height h, all starting from rest at the same moment. The objects are a thin hoop, like a wedding band, a spherical marble, a solid cylinder, which in this case would be a D-cell battery, and an empty soup can. In addition, a greased box slides down without friction. In what order do they reach the bottom of the incline? We'll take a look at that one. Do it now.
Okay, so here are our objects, and obviously we want to look at energy. Potential energy at the top, all these objects have is the same. It will be based on their mass. I think the mass are the same, so it'll be the same. the kinetic energy at the bottom will be our V, and then if we're trying to find V, that's where we're going to be at. But then we have to consider the moment of inertia, and for all of these objects, the hoop is this mr squared. The empty can is like a hoop earth, and this is very similar to a hoop. In fact, maybe just a little bit different, but we'll talk about that. The cylinder is 1/2 mr squared. The marble's 2/5, and of course the greased box. We know again that angular velocity is Vr, so I can put that in here, but that gives me V squared R squared, and that's where R squareds cancel. So we can get rid of R squared in all of these equations, and really the mass will disappear. So once we get rid of the masses, because mass cancels out in everything, what we're left with to find the velocity will be the number in front. So the hoop has no number in front, right? It has a 1. The hoop and thin disc, empty can, we'll get to that one. The cylinder's 1/2, the marble's 2/5, and of course the greased box. So the order will be based on that number. The box will be first because there's no friction. But the marble has 2/5 the velocity, right? That's 1/2, and then that would be, this would be 1, so the marble would be next. 1/2 the cylinder would be next. Now the empty can's in the middle because it's the hoop and thin disc. So the can is just like a hoop with a little bit more. So this number, right, would be a number that would be between 1/2 and 1. So that would fit in between the battery and the hoop. And then of course the hoop would be last. But the point is that we can look at the fraction to get to this as opposed to having to go through a bunch of math. And so again, multiple choice type question, maybe on an AP exam. Which one would go faster? Avoid trying to think about doing too much math and think more about what you can eliminate. In this case, getting rid of the R's and the M's leaves us with just with the fraction in front.